Welcome everyone to this episode on design and analysis of algorithms. In this lecture, we'll learn about greedy algorithms and we'll learn what connects Shah Rukh Khan or Mohan Bhargav in Charanpur, Swadesh movie, with Otakar Borufka in Moravia. It is minimum spanning tree. In this video, there are 4 parts. So in the first part in this video, we'll talk about introduction and a meta algorithm for minimum spanning tree. And then in the second part, we'll talk about 2 algorithms, Kruskal's algorithm and Borufka's algorithm. Third part, we'll talk about Jarnik-Prim's algorithm. And the fourth part, we'll compare different types of spanning tree algorithm and different extensions. And we'll also talk about more on properties of greedy algorithms. Okay, so let's start. Swadesh is a cult classic movie. In this movie, Mohan Bhargav or Shah Rukh Khan, he has this mission to connect every house in the village to an electricity power plant. This is the power plant, and there's a very emotional scene in this movie, this Bijli, the light when every village gets illuminated. So in this problem, Shah Rukh is at one point, and this is the place where the power plant is. And then there are several houses. Each of these nodes in the graph representing different houses. So maybe some house is for Melaram, some is for the Mukhya, and some are for other people. So each node in the graph represents one house. And the edge costs between 2 houses, it shows the amount of cost that you require to connect 2 houses by electricity wire, maybe the length of the wire. So his goal is to connect all houses to the power plant using minimum amount of wire or minimum cost wire, where the cost are edge cost. And if you think a bit, this is the solution. So there are 2 properties here. One, this is a spanning graph. So all the vertices must be connected. And this is also a tree, because if there is a cycle, we can remove an edge. It's just adding more cost and still the graph will remain connected. So what we are getting is a spanning tree, and our goal is to minimize the cost. This is minimum spanning tree. And this is exactly the problem which was solved by Otakar Borufka in 1926 in the context of some electricity power line network design problem for electrification of southwest Moravia. In his paper on a certain minimal problem, which was published in an electricity journal, Electrotechnica, this is the journal. And he discussed about this problem and proposed the first algorithm. We'll talk more about the history about the problem and different types of algorithms for the problem. But as this is a very fundamental problem, MST is one of the prototypical greedy algorithm problem. There are several people who independently and parallelly came up with multiple greedy algorithms, and we'll see Jarnik-Prim, Borufka, Kruskal, multiple algorithms. And all of them actually follow a meta algorithm and will prove the meta property for which all these greedy algorithms work. So now let's start formally with the definition of minimum spanning tree. We are given a connected, undirected, weighted graph. As we're looking for a spanning tree, we need the graph to be connected. We are focusing on the undirected case. There is no directed edges. There is a variant called arborescence, which we'll talk about later, but in this variant, we're only focusing on undirected graph. And each edge has some cost, which is a real number or rational number, let's say. So here the edge cost can be negative as well. Unlike some other problems which we'll see later, like Dijkstra's algorithm, which does not work with negative edges, this actually works with negative edges. So W is a function, which is weight or cost. We will use this interchangeably, which maps the edge to a number. And our goal is to find a spanning tree T. Spanning means it should connect all the vertices. Tree means it's acyclic subgraph. And our goal is to minimize the cost. What is the cost of the tree or weight of the tree? This is just sum of all the weights of all edges which are present in T. So we are summing over all E in T, WE. That is giving us the cost of WT. Now first let us think about more structural property. So given n vertices, what is the maximum number of spanning trees that can be there? it turns out it can be exponential. This is one example. If I have 4 vertex K4, then you can see there are 16 types of spanning tree. So which is 4 to the power 4 minus 2. And actually you can prove it that the maximum number of spanning tree a n vertex graph can have is n to the power n minus 2. And this follows from something called Kirchhoff's theorem or Kirchhoff's matrix tree theorem, which says the number of spanning tree is equal to any cofactor of the Laplacian matrix of the underlying graph, which is a generalization of Cayley's formula. So I will not talk about details about the structural properties or more combinatorial properties. If you're interested, you can read about that. But our focus will be algorithms. But only one point is, though there are exponential number of trees, spanning trees, our goal is to find the minimum spanning tree. And it can be done in polynomial time. In fact, in greedy way. So first, to solve a problem, we resort to the easiest case, unweighted graph. So say take an example, if I have C4, a cycle of 4 vertices, then there are 4 types of spanning tree, minimum spanning tree actually, which has 3, cost 3. Now you can do it by 2 ways. Either you can use, there are many ways, but at least it will work with DFS or depth first search, or BFS or breadth first search in almost linear time in the number of edges, order of V plus E time. I'm assuming you know DFS and BFS, but in case you do not know, just I'll probably post some later videos or some other materials where you can read and learn about this. So I'm assuming it's a second algorithm course, you already know about BFS and DFS. But then if you try BFS or DFS on the weighted case, it will fail. It might fail. Take this example. I have 1, 2, 3, 4, 4 edges, and then the spanning tree, minimum spanning tree is this one. So that's a homework question that actually, if you have distinct edge weights, then the graph has a unique MST. Then instead of so many possible spanning trees, only one spanning tree will be the minimum spanning tree. So if we think of BFS, then if we start from this red vertex, we'll explore all these edges which are leaving the red vertex. So in this case, 3 and 4. Then we'll explore probably 2 and continue. So we'll miss this edge 1. Similarly, if we start DFS, we'll start with 4, then go to 3, then go to 2. And okay, this figure is not completely correct, but you can make another example where this DFS will not work. So next question is then, what can we do? How can I find a greedy algorithm for the case which should still work? Now, what is greedy? Greedy means you start with something completely empty. At the end, you get the optimal solution. And in the intermediate cases, you make some greedy choices or myopic choices. You don't think in the long run what is happening. At this point, what is my best option? I just go with that one. I continue. So we have to show them this myopic choice is indeed optimal. For that, one option to show that algorithm always maintains a part of opt. So it grows as in a way such that always the solution that is maintained by the algorithm is a part of the final optimal solution. For that, we have a generic algorithm. And generic algorithm is you need to maintain an acyclic subgraph F, which is an intermediate spanning forest. So initially we are starting with, let's say, all isolated vertex. So there are n vertex, there are n one vertex trees in that way, the trivial trees, one vertex trees. And at the end, we are connecting all of them, we are getting a spanning tree. So in the intermediate case, we are still having a spanning graph, but it is not connected. So it's a spanning forest. And then the question is, how do we develop this F? How do we, in each iteration, how do we add edges? For that, we first define 3 types of edges. First one is useless edge, which we should not add. Second type of edge is called safe edges. We'll show that we can always add safe edges. It is fine. And third type of edges are the undecided edges, which are neither safe nor useless. So let's take one example. Let's say the left one is a graph. The red one is component 1, then this is component 2, this is component 4, component 3, and so on. There are 4 components. Now, if I look at this edge 10 of cost 10, this edge, both the endpoints of this edge are lying on the same component. So if I add this edge, we'll create a cycle. So there is no point adding this edge. So we call it useless edge. That's the definition of useless edge. If both the endpoints of the edge are in the same component, we call it useless. So in this graph, I'm using this brown color to denote useless edges. Now, if we look at each component and look at the edges which are leaving the component, and among them, the minimum cost edge, we call it safe edge. For example, if we take C1, the edges which are leaving is 13, 12, and 14. And among these three, minimum cost is 12. So I use 12 as a safe edge. Similarly, for C2, you can verify 12 is again the safe edge. And for C3 and C4, 15 is the cheapest edge which is leaving C3 or C4. So this is the safe edge. In this figure, green edges are the safe edges, and the remaining edges which are neither useless nor safe, we are using this color for that. Okay. So now this is the key lemma that we'll prove. And this lemma, just the single lemma, which is not too long, very short, will give a meta algorithm, and we'll see all the algorithms that we'll study. Kruskal's algorithm, Prim's algorithm, Borufka's algorithm are just variants of that meta algorithm where we're adding safe edges in each round. It's just which safe edges to add. There's an ordering that is different in different algorithm, but all we are doing is adding safe edges. And this lemma itself shows the proof of correctness for all three algorithms. So let's see this lemma. What we want to prove is MST of G contains all safe edges. In fact, we'll show a stronger version. Instead of showing, when you talk about safe edges, if you remember the definition, we are talking about a component and then looking at all the edges which are leaving the component and taking the minimum edge. But even if we take a more general case, not a component, but some subset of vertices, which may not be connected, which may not be a component, even then I want to show for any subset of vertices S of V, MST of G contains a minimum weight edge with exactly one endpoint in S. So there are several edges. Some edges will have both endpoints in S. We're not considering them. Some edges will not have any endpoint in S. That's also something which we will not consider, but we'll only consider those edges which have only one endpoint in S and the other endpoint is not in S. So let's say we call S to be S prime to be V minus S. Those vertices which are not in S. So one endpoint is in S, other endpoint is in S prime. And among those edges, the minimum cost edge, we call it to be, we prove that that edge is part of MST. And in fact, if it's a component, that is exactly the safe edge. So how do we prove it? First, we'll prove it by a contradiction. So let's say we'll go step by step and we'll prove some properties step by step. And if something is not clear, pause the video, spend some time and understand why it is true, and then you can progress. So assume that E is the minimum weight edge with exactly one endpoint in S. So think of this is a graph. And the red vertices are the vertices which are in S, and the remaining green vertices are in S prime, which are V minus S, which are not in S. So now if I consider some edges, this green edge, this edge which contains two green vertices, will not consider because both endpoints are in S prime. Or if I take this edge, again, both endpoints are in S, I will not consider. Remaining edges, if I consider, for example, which has one endpoint in S and other endpoint in S prime, among those edges, like this is one example, or this is one example, this is one example, this is one example, this is one example, and so on. Among these edges, we consider the one which has minimum cost and consider that to be E. So E is the minimum weight edge which has exactly one endpoint in S. And we want to show this is part of MST. So for contradiction, we assume it is not part of MST, and the MST we define to be T. Now, as MST is connected, it should contain a unique path between U and V. So first of all, in MST, the graph is connected. So you can reach any vertex to any other vertex. So there is always a path. And it's a unique path because if there are two paths, you can reach U to V via one path and then V to U via another path. That will create a cycle. But it's a tree, there is no cycle. So there is a unique path between U to V. And as U is in S prime, as U is in S prime, it's not in S, and V is in S, if we walk along the path, at some point the flip happens that one vertex is part of S prime and other vertex in the edge is part of V. So that's the property 3, that there must be an edge E prime such that one of its endpoint is in S prime and other one is S. So think of in this graph, I have used the yellow color to show the path from U to V in the tree T. In that case, there can be either this vertex we can take, which has one endpoint in S prime, another endpoint in S, or this vertex, this edge, where one endpoint is in S prime, other endpoint is in S. So what we claim, there must be at least one edge such that one of its endpoint is in S prime and other one is in S. There can be multiple. In this case, there are multiple, but at least one such edge will be there. Once we get this, then we consider again further. So we know that the tree T is acyclic. So if I delete or remove the edge E prime from this tree, we should get two components. One will contain U, one endpoint of E, and another will contain other endpoint of E, which is V. Think of this was the tree. This orange one was the tree along with E prime. Now, if I delete E prime, then I get two components. One is this, other one is this. Okay, because this was a tree, any edge I delete, the graph will become disconnected. And in the left part, every vertex can be reached from U. In the right part, every vertex can be reached from V. But the vertices which are in the right and left, they cannot be reached from each other. Now we claim that let's add E into it. In the fifth step, we say, let's add T into T minus E prime. And we claim this is also a spanning tree. Why? If I look at this case, I add this edge between these two parts. This was T minus E prime, and I add E. Now, why it is spanning? Remember, everything was connected here, everything was connected here, and now we are connecting here. So all vertices are connected in the tree, because in the left side, if I take any vertex, and if we take another vertex right side now, from left side any vertex I can reach U easily, and then from U I go to V via E, and then I can go to the vertex in right side from V. So every vertex can be reached, and this is spanning, and this is also a tree. There is no cycle because we are adding this edge. These two are earlier disconnected, and there is a unique edge we are adding. So this is not creating any cycle. If there is a cycle, then we'll get two different paths between U and V. That is not there. Only one path we are adding. So it is not creating any cycle. It's a spanning tree. Then if we look at the cost of this tree, Wt prime, that is Wt minus W weight of E prime plus We. But we assumed that among all edges, which have one endpoint in S and one endpoint in S prime, E was the cheapest one. Both E and E prime are such candidate edges, but by assumption, we have E to be the cheapest one. So W of E prime is more than W of E. And from that, we get that weight of T is strictly more than W of T prime. So we see that T prime is a spanning tree, and it has cost lower than the minimum spanning tree T, which is a contradiction because then T prime should be the minimum spanning tree and not T. So we arrive at a contradiction, and that proves our lemma. So in this lemma, if I use S to be a connected component, we get that MST contains all safe edges. And this is the lemma which provides us a meta algorithm that keep on adding safe edges. In fact, there are three different variants. In Kruskal, the algorithm is you scan all edges by increasing weight, and if an edge is safe, then we add it to F. So in this graph, for example, we take the smallest edge 2, then we add it, then 3, then we add it, continue. And if there is some edge which is not safe, both the endpoints are a part of the same component, then we don't add and we continue. We'll go over this Kruskal in more detail in the next lecture. This is just high level idea just to show all three are doing the same thing. Jannik prim, we start with a single vertex here and then we grow. The safe edge which is leaving this component, we're always maintaining a tree. And finally we reach this one. And in Borufka, we start with again all different disjoint single vertex trees, and then we look at the safe edge for all of them, and we get maybe for this vertex this is a safe edge, for this vertex is a safe edge. So all these safe edges we add at once, and then we get this component, two components. In the next round, for these components, we add their safe edges at once and continue. So this is the algorithm which Borufka, the first spanning tree algorithm, which was proposed. So in the next part, we'll talk in details about Kruskal and Borufka. In the third part, we'll talk about Jernik, Prim, and for the fourth part, we'll talk about different comparisons and different extensions and other problems. Thank you.